For this half reaction, the bromate thing that we just open the standard electrode table. A, write the cell shorthand notation to determine the standard electrode potential of the half reaction. And B, write the Nernst equation. So let's do the A first. Write the cell shorthand notation to determine the standard electrode potential of the half reaction. So we just learned, right? The definition, we have to put She on the left. And then you have to put this one on the right, right? So your cell shorthand notation is going to be, so we're going to start with the left first. So I think you should be able to remember now that the standard hydrogen electrode use the platinum as the inert electrode. So it's going to be platinum solid. And your She has proton and hydrogen gas. Oh, sorry, proton and hydrogen gas. It is the separate phase, so I'm just going to use a single vertical line. So this is the She. If it's in the standard condition, we don't have to specify the concentration, but if it's something else, you need to. And now your right is going to be this half cell. What do you have in this half cell? You have bromate, you have proton, you have bromide. So, but you don't have any solid electrode. You don't have any solid conductor. So you need to add the solid conductor, the inert solid conductor like platinum. So you divide this half cell with the salt bridge, and then you put something else, which is bromate, proton. It's in the same solution, so I'm just going to use comma and bromide ion. And then you need one solid conductor, which is inert. So I'm going to use platinum. Sometimes you can use carbon as well, but I'm just going to use platinum here. Yep. So this is the answer for this one. Because we don't have the solid conductor here, so that's why we have to put platinum as the inert conductor, inert solid conductor. So this is the A. The B, write the Nernst equation for the potential of this half cell. So we just learned, right? So it's going to be electrode potential is equal to the standard electrode potential of this one, which is bromide, minus, let's use the form at 25 degrees Celsius to make our life easy. In any temperature, it's going to be RT over NF, right? But this one, we just going to use, oops, sorry. Yeah, we just going to use 0.0592 over what? Over which number should be in the denominator? It's n, right? And this one n is equal to what? To 6, right? To 6. And then once we use the 0.0592 thing, we're gonna use the log base 10. And then you write the chemical equilibrium constant of this one. So on the product side, you have only bromide. And water is pure, so we don't include it in the reaction quotient. But the denominator you have bromate, right? And proton. But your proton is 6, so it has to be like 2 to the 6. And sometimes you can just plug the the table, the value from the table. So this is gonna be 1L 1.44, and yeah, this term. Yeah, the exam will ask you to write something like this, but then it's online, so you can guess how I'm gonna do this. Yeah. So this is the answer. Any question? Okay, good. I'm gonna go to the next one. So the second example, the example 1.2 here is write the Nernst equation of this half cell, of this half reaction to show that when multiplying the whole half reaction, standard electrode potential still stays the same. So let's write this one. So for this one, the Nernst equation is gonna be E equal to E silver plus silver, right? Minus 0.0592 over 3, because now the this one is 3, the n, the number of electron is 3, log silver metal is pure, so we don't include it in the Nernst equation reaction, Nernst equation, but silver here is solution, so we have to include it. So the this one is gonna be 1, right? But the denominator is gonna be silver. But since this one has 3 to it, so you have to put 3 in the exponent. All right, but now we have to rearrange. So this is gonna be the same, and then this is the exponent, right? And then you can use the properties of logarithm. I'm gonna use this. So log. So this is 1 over silver to the third. So I can write this, right? 1 over silver and everything to the third, right? And then I can take it out from the log, right, by multiplying here. So this is gonna be still 0.0592 over 3 multiplied by 3 of log over log of the 1 over silver. But now you have 3 here. You have 3 here. We can just cancel each other. So you get E equal to E naught minus 0.0592 over 1, basically log 1 over silver, which is the Nernst equation of the silver plus electron, and you get silver solid. Yep. So this is to show. So this is all for this example. You use the properties of the logarithm to show this one. Any question? All right. So let's do the next example. The next example, this is the only place that I want to show you that activity coefficient matters, but we are not doing it in the exam, but this one, let's do it. Calculate the half cell potential of this one, nickel sulfate at 25 degrees Celsius by comparing using concentration versus activity and given gamma or activity coefficient equal to 0.2. So we have to do it in 2 ways. The first way is using just concentration. So write the Nernst equation is this one is nickel 2 plus, right? Plus 2 electron and you get nickel. So the Nernst equation of this reaction is E equal to E naught of nickel 2 plus nickel minus 0.0592 over what? This one has 2. So we put 2 log 1 over nickel. And you plug everything. So can you open the standard table for this one? What is this one? Can you type it? What is this one of the nickel? Minus 0.25, thank you. Minus 0.250 minus the whole thing. 0.0592 over 2 log. The concentration of nickel 2 plus is equal to this one, 0.27. Yep. And you plug the number to the calculator, you get something like 0.267 volts, I believe. So this is when you use the concentration. But if you use the activity, let's see, the Nernst equation by using the activity is the same thing, except you change the concentration to activity. So this is gonna be the standard electrode potential minus 0.0592 over 2 log 1 over activity of nickel 2 plus. And activity is equal to the coefficient multiplied by the concentration. So I'm gonna plug everything. It's gonna be same number on the front, but now the denominator, you're just gonna have 0.20 multiplied by 0.270. 0.20 is the activity coefficient, and 0.27 is the concentration. And you plug the number, and you get, I believe it's minus 0.288 volts. So you can see that by using concentration and activities, the potential, the difference in the value is around 21 millivolt, which may be not too much in some application, but it's a lot in another applications. So that's why sometimes you can see people use just concentration, and some people use activity as well, especially when you work with high concentration thing, high concentration. 0.2 I think is high enough. But if you work with like something like millimolar, it's not high, it's fine. This is just to demonstrate you. Again, I don't test this in the exam or any question, but it's good to know anyway. So this is example 1.3. Okay, we have 2 examples left, so let's do it. Any question before we are moving to the next one? Okay, so I'm gonna go to the next one. The next one, calculate the, why in the question 1.2, the reaction quotient is 1 over silver to the third. Because we want to write the Nernst equation of this one. 3 silver ion plus 3 electron, you get 3 silver. But here you see that the silver ion has the stoichiometric coefficient of 3. So you have to put 3 here, right? This is kind of the equilibrium constant. It's the same form, so that's why you have to put the stoichiometric coefficient in the exponent. Does that answer your question? Okay, so example 1.4, calculate the cell potential of this one. If you use the method from your Gen Chem, you can combine this together in one Nernst equation, right? But sometimes it can be very complicated in each electrode or in each half cell. So I prefer you to separate it into 2 electrode potential. Because we want to do like E cell is equal to E right minus E left. So we're gonna write the Nernst equation for each part, E right and then E left, and then find the number and then do the subtraction later. So what is E right? E right is the standard potential of silver ion and silver minus 0.0592 over 1, I believe, because this is silver plus electron, you get silver. Log 1 over silver plus. So the number, I believe, is 0.799 minus 0.0592 over 1 log 1 over 0.0200. So if you use your calculator, you will get something like 0.698 volt, I believe. So this is the E right. So what is E left? E left is almost the same, right? Except the coefficient is not the same. So this one, the reaction is copper 2 plus 2 electron. You get copper. So Nernst equation of this one is copper 2 plus standard electrode potential of copper 2 plus copper minus 0.0592 over N log 1 over copper. And then you plug the number again. This is 0.337 minus 0.0592 over 2 log 1 over 0.02. And you get 0.2x7 volt. So we already get everything that we want. So the cell potential or E cell is equal to E right, which is 0.6x9 minus E left, which is 0.2x7 volt. And you get 0.411 volt as your answer. So you have to have the skill that to recognize the half reaction from the shorthand notation, and so that you can write the Nernst equation from it and then plug everything. This is not hard. The last example here, the last example today, the same question. Calculate the cell potential of this one. But now it's more complicated because I don't put the saw bridge. We don't have the saw bridge here because this is like the cell without liquid junction, right? And then you should be able to separate two half cells from this. And then you can see here that here you have silver. You have silver chloride. So this may be one half cell. Another half cell you may have, hydrochloric. So hydrochloric basically gives you proton, I think. And it gives you chloride as well. And this one is hydrogen gas. This one is hydrogen gas. And platinum. Platinum is kind of the inert electrode, so I don't think we use it. So now we can see that what two half cells that we have is the silver chloride half cell and the hydrogen plus and hydrogen half cell. So this is the left one. So this is the right one. Yep. So this is the right one. So again, E right. If I go too fast, you can go back, watch it later, right, in the echo. So E right is equal to standard electrode potential of proton hydrogen gas minus 0.0592 over what? To know this, you have to like either write the half reaction, or you can just go to see the standard electrode potential table and use the N from that, which is maybe more easier. And you will get that the N is 2, yeah. And log. And it's actually this one. Oops. This one, right? And hydrogen is the gas, so you need atmosphere, you need the pressure instead. So this is pressure of the hydrogen gas over the concentration of proton to the second. So you plug the number. So the standard electrode potential, this is actually She, but so it is 0 minus 0.0592 over 2 log. Pressure of the gas is 0.800, and the concentration of the proton is 0.02 to the second. So plug the number in your calculator, you get minus 0.098 volts. For E left, it is this one. So you can find the potential of this from the table. So the reaction is basically silver chloride plus electron. I think you get silver plus chloride. So your product gonna have silver and chloride. Silver is solid, so we don't include it. Chloride is aqueous, so we include it. The reactant, silver chloride is solid, we don't put it. So this is the Nernst equation of this left half cell. So you plug the number. So this is 0.222 minus 0.0592 over 1 log. What is the concentration of chloride? So you can see, okay, hydrochloric acid is 0.02 molar. So this is the same number, which is 0.323 volt. So that's E right and E left. So we're gonna find E cell, right? E cell is equal to E right minus E left, which is minus 0.098 volt minus 0.323 volt, which is minus 0.421 volt. So it cannot be operated, basically. Any question for this one? This one is more complicated because you need to separate it into the half cell because there's no solvent to see here. And then you have to choose the right standard electrode potential from the tables. So it requires you more skills on this one. Any question? Why does we always use platinum as the inert metal? Why not other metals? You're gonna learn it later that a lot of metals like copper or zinc is too reactive. So if your solution may be acidic, then it's gonna corrode your metal, right? So you cannot use it for too long. But for platinum, it has the special properties that it's not so reactive. So we always use platinum as the inert electrode or inert metal. We kind of pretty confident that if we put platinum in any solution, it will be fine. Yep, I think that's my answer.